we have established that we can look at the y variable in the linear model as a linear combination of basis vectors using an orthonormal basis, where we select that basis so that the first R of those U's span the space spanned by the X matrix, and the first Q of those again span the matrix, span the same space as the Z matrix, so that we start with the Z space, move up to the X space, and then to the Y space. Also remember that when we look at the coefficients of Y in this new space U1 through UN, each of these zeta hat i's is simply the inner product between Y and UI. And this is easy to see. You just take U inner product to this quantity, same as U inner product to this quantity, and you're left only with Ci hat. So this is the coefficient. Now also next, remember, for example, that we have written this as an element of this V here, span of the X matrix. So this is an element of V, this first part, and then the second part is orthogonal to V. And so what we have done here is we've actually split the Y into two parts, an X beta hat plus an E hat. And these two are orthogonal. Now then, of course, if we write X in this basis, the coefficients of X beta hat are going to be UI X beta hat inner product with UI, if you like. Now, but the coefficient of Y in the same system is Y itself, inner product UI, as we said before, and that's equal to X beta hat plus E hat inner product UI. So, and now this one here is in the perpendicular space, remember? So this is in the perp. So this is the same as X beta hat inner product UI. So we get the same coefficient for these U's for the X's, X beta hat, as we get for the Y's up to that point, and exactly the same logic applies to C gamma hat. And because we get the same coefficients everywhere for the first U's, we also see that the projection of X beta hat onto W, onto the span of the Z space, span of the Z matrix, the projection of X beta hat onto that is going to be Z gamma hat. So it doesn't matter where we start with Y, project that onto W, or start with X beta hat and project that onto W. So in other words, we can project the Y first onto X beta hat, then that onto to get zeta gamma hat, and we get exactly the same result as if we had projected Y directly to get C gamma hat. So that's pretty cool. And that forms the groundwork for the next steps. We now want to write the Z's in such a way that we see easily what the zetas, sorry, the Greek zetas, in such a way that we can easily work out their expected values and so forth. So what we're going to do is we're going to take these each of these zetas, remember, is equal to, okay, let me see now, I need to do a right screen here. So each of these zeta I hats, we can write as y inner product ui. Now, or equivalently, ui inner product y, or equivalently, think of ui as a matrix, take the transpose of that matrix. So in other words, this was an n by 1 matrix. This is now a 1 by n matrix. And we do matrix multiplication with the y, thinking of y as an n by 1 matrix. So n by 1, there we go. Now, if we then order these ui's, put them together into one big huge matrix, u1, u2, all the way up to un, and we call this a Q. Then we have found that Q transpose Y, if we write Q transpose Y equal to Z, that this result is actually zeta 1 hat, all the way to zeta n hat. So we have a very simple way of writing the zetas as a function of y, and now we know that the expected value of this z vector is the expected value of q prime y. So this is equal to q x beta, or q times the expected value of y, which is x beta. And we also know that the variance covariance matrix of all these z's is q prime times the variance covariance matrix of the y times q, and this now is equal to q prime sigma times the identity times q, or simply q prime q, and you know, if you write q prime, it's got this u on the side, so q prime q is the identity matrix, and so this is, in other words, sigma squared times the identity matrix. So the z's are uncorrelated, and they have expected value q times x beta. And our next step will be to expand on this and notice that, of course, you see that right here. If we assume that the y's were multivariate normal, then this is a linear transformation of a multivariate normal. And so this set here, this collection of zetas is also multivariate normal. And that will give us the results we need to find all the distributions of everything that we need and to do the actual tests. But one step at a time.